young age. He's a high school junior, but he's been passionate about vision impairment all his life. He's been putting his mind to how to build an innovation. So he's brought about several interesting features which we talk about, like echolocation, machine learning, and building vision into kind of a device. And the most exciting thing about a device like that is its price. So we really haven't set the final price yet, but it's probably going to be like a 10th or a 20th of the cost of comparable devices today. So Sid has actually gone to 3 Vision Aid centers in India and done some field testing there. So I'm now hand off to Sid to talk about what he's done.
Thank you. Mumbai, India, 4 years ago. I was on a train in Mumbai and a blind woman walked in. She had her cane and she was hitting it against people, chairs, luggage. She was having a hard time finding her way. I saw this and I wanted to do something to make a change. 285 million people live like this every single day. These people are either legally blind, meaning they see an image like this, 20/200 vision, or worse, even with the maximum magnification in their eyeglasses. Or they may have a splotch in their eye, like in the right picture, or a peripheral vision range of just this one. In addition, 39 million people are fully blind, meaning they can't see whatsoever. So I saw this problem and I wanted to make a change. And in 9th grade, I invented the device called Seeing for the Blind. It's a pair of glasses. The part is covering it now, but it's a pair of glasses that uses echolocation and machine learning to help the blind find their way. And using these two things, it is able to give full spatial awareness to the blind, and it allows them to navigate with ease. So let's define what spatial awareness is. Full spatial awareness. The way the blind navigate, at least from the perspective that I've heard from most people, is that they create their own 3D understanding of their surroundings. And then they know what objects are around them and where those objects are in relation to them. And so with that, there are 2 fundamental components, the what and the where. We want to know where things are and what they are. I know that there's something right here, and I know there's something right here, but now I know that there's a laptop here and a backpack here. And what we're really trying to do is create a device that is able to accurately convey both these 2 informations to the user so that they can understand their surroundings easily. So let's dive into the where first. Let's talk about how we can convey the where of surroundings. So we're going to use a technology that's called echolocation. And in this technology, you'll have a sender and a receiver. And this sender will send out sound waves, and these sound waves will travel at a very fast speed. They'll bounce across onto an object. In this case, we're going to call the wall on the back. They'll bounce off the wall and come back. And we can measure the time it takes for the sound waves to go. And from that, we can calculate a distance measurement. We can calculate a distance between myself and the obstacle that I'm measuring. And based on that distance measurement, we have to then convey it to the user in a way that they can easily understand it. So we're using a technology that's called Arduino. This is a low-power microcontroller that takes in an input, does some function, does some mathematical operation to it, and gives back an output. It's a very simple device, and what we end up doing is we put in our distance measurement, we apply a function to it, and this function will give off a sample output. And in this case, we're going to give the output feedback in the form of auditory and tactile feedback. So for each distance measurement, the function will calculate a unique auditory and tactile measurement that will then be outputted, and that the blind users can then use to understand where things are in their surroundings. So the first one we'll look at is auditory feedback. Right here, you can see this graph. What we're doing is we're giving off these beeps that tell distance. And when we give off these beeps, we're going to change 2 things: the pitch of the beep, meaning the frequency, the note that the beep is playing, and then the time that's in between each beep. And when we do that, we'll be able to simulate an understanding of relative distance. Here's an example. So we will stop when you're freaking out. Exactly.
So what you're trying to demonstrate is as the pitch gets lower and the beeps slow down, they know to stop?
It's actually the opposite. As it gets higher, then they'll know that there's something in front of them. So if you have a high-pitched beep that's going really fast, you know that there's something in front of you. And when there's a low-pitched beep, there's something further away. So That's how the auditory feedback works. In addition, there's also a tactile output where we can give vibration as well. So here we have a graph that's showing that, and it's showing that as you come closer towards an obstacle, there'll be more vibration that you can feel.
Excuse me?
Yeah.
What about backwards? Like you see that example video you show us?
Yeah.
When the person was falling back, there was not only the obstacles in front of him, there was also an obstacle like there was a glass fence back of him. However, I don't think you have something that would actually detect all of the surroundings. Like you have to turn around and to make sure, okay, that was the front obstacle.
Right.
What if it doesn't?
Yeah, so this device is mainly used to just tell what is in front of you itself, and it's based on your field of vision itself. So if I'm wearing the glasses, it's supposed to be built to be more intuitive for a user who is used to have experienced sight before. That's people who are blind at birth, and it's 80% of the blind population in the world. And it's based on in the direction that you're looking at. Exactly the direction you're looking at, that's what's captured in the camera. So yeah, you can't see what's behind you, but it's more intuitive to have this thing where it's exactly in the direction in which you point your head, that's the direction you can end up getting. But yeah.
So then, as someone who is uncongenitally bilateral blind, but I don't have necessarily what's called a spatial awareness problem. Like, so there are some blind people who have a spatial awareness issue where their version of, looking straight ahead might be like this, where they're basically looking down as they're walking. So then how do you, the object will then always detect something because they're almost looking at the ground.
Right. Yeah, that's one issue that this device does not account for itself. Since it's not a pair of glasses, it's only meant just for in the direction in which you're looking forward. But there are some certain parts of that, so certain parts of problems that can be solved by other devices, which I'll get into later in the presentation. But yeah, so the way the main system works is that you'll take in a distance measurement, you'll have an analysis, and then you'll give off some output. So let's try an example with this by imagining that we're looking at a blank space. We don't know what's in front of us. And we're going to hear two different auditory outputs, and we're going to try to see how far away these objects are. So here's the first one. It's really quiet. I don't know if there's a way to increase the volume. Okay, so basically that was a very low-pitched sound. And then we can hear the next one afterwards.
You can hear it in the front here, I'm not sure about the back.
Can you hear the, okay, so the first one you heard was a very low-pitched sound. The second one you heard was a high-pitched sound. Let's hear the low-pitched one again. So this is what it's telling us. Because the sound is low, we can tell that there's some object that's far away. And let's represent this object with a dot. And we can say this is an object that's far away in our surroundings, but it's not that close to us. Let's hear the second one again. So this is telling us that there's some object that's close to us because the pitch is very high. So we can create this object here where it's very close to us. Now what this is going to do is it's going to allow us to create this understanding of what exactly is around us by using the relative pitch to give ourselves a relative distance. And now we can know how far objects are in relation to us. Here's an example of this working in a real-life situation. So what that allows us to do is it allows us to know where objects are in relation to us. However, that does not tell us what those objects are. So it only gives us half the picture. So to do that, we're going to dive into the what next. So the way we do this is by using something called object identification. What this does is we'll have an object, and a machine learning algorithm will look at a picture of some image, and it will identify what the object is. So in this case, if you have a person, it will say that it will classify this image as a person. And the way this works is we're using something called Raspberry Pi. It's like Arduino, except it's another low-powered computer, and it can actually run machine learning algorithms on it. So we're running a deep learning convolutional neural network for image recognition, and it's taking in an image from that camera and processing it. So this is what the live image would look like as it works. So this is, you can see here that it's classifying different objects, and it's drawing a giant rectangle around them. So in this case, it's classifying this right here as a bed, and then behind it is classifying that as a laptop. So it's able to classify these different objects based on a set data set that is programmed into the neural network and is trained to recognize. And as a result of that, it can then recognize certain objects, classify their names, and it can read it back to the user. So let's imagine, go back into our space where we can't see, and let's try to identify different objects again. It's even quieter, but it's a potted plant. So we can imagine that there will be some potted plant somewhere in our image space. Let's try it again. Also quiet again, but it said book. So we can imagine there's going to be a book right here. And based on that, we are then able to know what objects are around us. And now we can try to imagine this back in our example.
Maybe if you could repeat it, because you can hear.
Yeah.
What
Book.
it's saying.
Book. Book. Person. Couch. Person. Person. Laptop. Couch.
Now, is the
Laptop. Sorry?
is the idea that you would use this as a supplement? So while you're traveling with your cane, you have your glasses on,
Yeah.
and then there'd be something connected to your ear.
Yeah.
Exactly.
That would be the supplement. Yeah. So in this case, you're using this is what that was telling you is the what, and it is. And I know what you're trying to get to that it's not. You don't really know exactly how far that distant that object is as well, away from as well. But that's when we can take the where and the what, we can combine them together. And now if we combine these two systems together, we can hear both the pitch sound and we can hear the beeping sound and the name of the objects. So here's a very low sound. And this is the computer saying it's a potted plant. So we know it's a low sound, it's far away, and we can think it's a potted plant. So we can think of a plant being far away in our image space. We can think there's a plant somewhere in the back of the room. Now we can try it again. So this is giving us another high pitch, meaning something's close by, and then we're hearing book. And so then we can say there's a book that's close to us. And based on that, we can know, we're then able to know the relative distance between different objects and know what those objects are specifically. So here's another example. Book, couch, book, person, potted plant, couch, person, book, 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 wine glass, laptop, suitcase. So based on that, we are then able to create a device that is able to combine two systems, echolocation and machine learning, to enable this the user to then understand where and what objects are around them, and then using that, they can then have a greater spatial awareness of where things are. Now, there are some other devices that are already out there that I like to compare this to. One of them is called the sonar glass. I don't know if anyone's familiar with that, but it basically is the echolocation component to this glasses. Basically, if the sonar glass, the way the sonar glass works, as I walk towards an obstacle, if I get too close to it, it will start vibrating, letting me know that there's something in front of me. Another device is called OrCam. This is a $3,000 to $4,000 device that basically has you attach it to a pair of glasses. And what happens is whenever you want to take a picture, you take a picture, and then if there's any text that in the picture that it's taken, it will read you the text. Another device is called Aria. And how this device works is you have a camera, and it connects to a smartphone. And whenever you want to know what's going on around you, you press dial in, and then it will connect you to a call center. And someone will be viewing what you're seeing through the camera, and based on that, they can then walk you through the surrounding around you. And then the other one that's out there is Microsoft Seeing AI, which is a smartphone app that just tells you the names of objects around you. So what these devices all do is they're able to do either telling you where or telling you what, but they're also not really fully combining the wearability and the full independence of the user. But this is also some other technology that's out there. And there's a lot of technology that's out in this that enables these devices to be made. However, the devices can't be fully robust and useful until they've gone through thorough feedback and user testing. And so thanks to Vision Aid, this summer I was able to travel to India to the Arvind Eye Care System and the Vision Aid India facilities in Vizag and Madurai. And then there I was able to conduct testing on my device and see how well it actually works. And here's a video from one of the testings we did. So, from the feedback, we got lots of valuable feedback. And some of this included things like a small form factor, wearability, having it intuitive for the blind user, a customizable data set of objects, relative scales for echolocation, and ground level object detection. And I will dive into each of these more in detail now. So for the first one, we have small form factor and wearability. So this entire device fits within the pair of glasses itself. The glasses I'll pass this around after. They're very lightweight. Most of the weight is actually in the secondary belt pouch. And in the belt pouch, we have the computers and we have the battery. And the battery is most of the weight. Now, it's a pretty compact form factor because you can just clip it onto your belt or you can just hold it. And it is hands-free when it's clipped onto your belt. The issue is the battery is the heaviest component, but the battery is also the users also want a long-lasting battery. So there's a trade-off between battery life and the actual portability and small form factor of the device. However, if you can get a battery that can last around a day for a day's worth of use and incorporate that, then the device can be much more compact and have a small form factor. In addition, in the future, the entire system can be built to be integrated within the glasses itself, so that there isn't any belt pouch, there's no wires, everything is just in a pair of glasses. But that will take some more time to get to that point. The other thing that was brought up in this during the feedback was that it was a very intuitive device to use. So the reason why the device is on a pair of glasses as opposed to actually being a handheld device, one is about the wearability, and the other is about intuition. So 80% of blind people are blind after birth. And for them, and for even those who are congenitally blind, it is very intuitive to move your head around to see where objects are around you. So, for example, if you want to see what's going on here, I would turn my head and see. But if I had a handheld device, it would be less intuitive to actually move my hand in that direction. So in addition to being wearable, it's also intuitive. In addition, there's also a customizable set of objects. So when we have the machine learning algorithm, we have a data set of pre-programmed objects, and then the neural network is trained on those objects. And we can just either add or subtract objects whenever we want, and then when we do that, we can just retrain the algorithm, and then it can recognize even more objects. That sounds like a pretty great deal to me. Apple, laptop, person, fork, we can add all these objects into there. Except, as you keep adding more and more objects, your data set gets larger and larger. And as your data set gets larger, the actual accuracy decreases. So you can't keep adding too many objects to the data set. We have to actually curtail and have a small amount of objects in order to keep this very accurate. But that means that if we have to choose the objects, we have to choose the objects that we have to have a certain set of objects for the device. But because different regions have different objects in their surroundings, we can customize the device specifically for a specific user. So for example, in America, we have a lot of stop signs. But then in India, there's not as many stop signs on the roads. Instead, on the roads, we have these rickshaws. So in the Indian model, you don't have to include the stop sign in the data set. Instead you can have rickshaw. In America, you include stop sign instead of rickshaw. So we can do that to basically have customizable data sets that the machine learning algorithm is still accurate while being specifically tailored to that user's surroundings. In addition, you can also change what the computer tells you as an output. So in America, we call this a flashlight. but in India, it's called a torch. So we can change the name that it tells you in the output, so that you can change the name that they tell you in the output, so that if I'm a user in India using it, it's more accessible to, it's more useful for me in what the output is telling me. And that also goes the same way with having different languages. Apple, same.
So, who can customize this? Can the user, or does it have to be sent back to someone,
Or
you know,
even like
you?
while you're selling those things, probably having different versions. Or pre-coded before
Yeah.
you put it in the market.
Yeah, so the one thing we can do is you can pre-code it before you do it. There's nothing stopping you from just taking the device itself, plugging it into a computer, and just reprogramming it to say different words. But I would say in terms of this, where you're actually adding different objects to the data set, that would probably be done by the manufacturer itself to send that out. But that can be done based on surveys and which objects they want to have, and then we can have those objects and put into the data set beforehand. And if more objects want to be added later on, they can do that as well. Yeah.
So it can be individualized as opposed to country or region.
Yeah,
It can be based on my life and what's important to me in my environment and my daily
Right.
living.
Yeah, so definitely, it can definitely be individualized. That would require an infrastructure it would require something like infrastructure to allow for the user to say what objects they want, and then that can be put into the data set. But yeah, and in fact, one of the things I was looking at as well was in the future I wanted to incorporate facial recognition, so that you can, because your glasses is a data store since you have a camera, you can take in images of the faces of loved ones, and then if there's an infrastructure set up where you can have neural networks that are trained for specific faces, then you can have the faces of loved ones being already programmed into the glasses. But yeah.
So how do you accommodate a non-English speaking?
Yeah, so that's one of the other things. So the way the program works, it actually identifies the objects in English itself. But when you actually go to speak the actual name of the object, you take what we were doing in the examples you saw is you took the English name, we just said the English name. But we can also just go and change the name as itself. So we can change flashlight. We can just on the computer we can just delete that and type in torch instead. Same thing for languages. So if we have Apple, we can call it save, and we can just change the name in the actual program itself, so you can get it to work for any language pretty easily. So there's also okay.
What about for people who are deafblind? How are you doing is your output primarily auditory, or you have some kind of haptic or braille touch output that's possible to connect to?
As of right now, no braille touch output. The only haptic output is in the echolocation. If you're telling where objects are, there is a haptic component for that. But yeah, for this, for giving the actual name of objects, that's a little harder to do with braille haptic. But I'll look into that.
Cool. Thanks. Sorry?
What about, or you get it to sync for braille display in the meantime?
That's what I was thinking, yeah.
Yeah, that could be possible.
That's what I said, the braille touch.
We're giving you lots of ideas.
India is a great country to do testing, because you could be walking down the street and suddenly you'll see an elephant or a camel or a cow, which you won't see here, depending on which part of India you live in. So this device has to go through a lot of testing, interesting use cases.
And uneven traffic.
Yeah. But
Complicated.
definitely.
It's complicated.
But the user, the person can also choose, if they're going to stay home, choose a one set of data to compare versus if they're going outside.
Yeah, that could be done as well. Definitely, yeah. As of right now, when we do initial production, it would just be like one set, one data set specifically tailored for an India market. But as the device ends up taking off, and we can actually create infrastructure that allows it, so that maybe there could be an app, and you can actually just put in the things you want, and you can update with the software update, and then you'll have specific objects for each person. So it'll be individualized. Yeah.
A lot of potential.
Yeah, a lot of potential.
Yeah. So and then there's a relative scales for echolocation. So the main idea is that you care more about objects that are closer to you than objects that are farther away. So what we want to do is we want to enhance the differences in distance at closer distances rather than at farther distances. So if you go back to our echolocation graph right here, this is superimposed with both tactile and auditory feedback. If you look at the orange line here, you'll notice that it's not a straight linear curve. Instead, it's a piecewise function that's segmented into two linear graphs. And the reason for doing this is that we want to highlight distances at closer levels. So here, the slope is much greater than the slope initially, and basically it means that I have a larger interval for in terms of pitch and frequency for distances that are closer to me rather than the ones that are further away. And this is able to then highlight objects that are close to me so that I can see the differences more easily than if it's something that's further away. And the same thing can be seen as well for vibration. In fact, the vibration graph here, which is the yellow curve, you'll realize that it's segmented into three piecewise linear graphs. And the reason why the first graph has a slope of 0, or in other words, there's no change at all in vibration for an object that's 4 meters away from you, the reason for that is because if you've ever sat in a massage chair, you'll notice that as you keep increasing the intensity of massage, you start to feel less and less because your body becomes more numb to tactile feedback. So that's why for objects that are further away, there's no change in tactile feedback, whereas for objects that are closer to you, the interval is much greater and is much more noticeable. In addition, if you're also walking around, since you're accounting for the vibration of your feet touching to the ground as well, you have to have some strong feedback that's noticeable enough for you to notice that. So the last one was ground level object detection. So this device is mainly working at the eye level. The way the sonar works, it has a conical degree of 15 degrees. And it's basically just a cone that extends outward, and then everything that's in this, any object that's in this cone will be captured. But this means that if I'm standing in this direction, I'll only be noticing the TV. But if I'm standing here, I couldn't actually see the laptop that's here, and I end up walking into it. So one of the solutions to this was to create ground level object detection. So what this is doing is the same system, but on the shoe. This is actually a custom built rig that can be velcroed onto any type of shoe. It's currently a prototype right now.
I doubt that. This is too complicated. Imagine somebody.
But yeah, there's but what this ends up doing is it allows you to know the distance between objects that are far away, that are on the ground as well. So as a result of that, you can then be able to know any objects that exist both on the ground and at the eye level. There is a blind spot right here between the ground level and the eye level, but this is under the assumption that there won't be many objects that are floating in the air. If something sits there, it has to have some connection up or down. In the case of this table, for example, there'd be the legs, and then the sonar would pick up the legs, and I can see that even though the table is right here. But after we can do comprehensive testing with both the eye level and ground level obstacle analysis.
Actually, 1 second.
Yeah.
This thing is that the top device will have 15 degrees of the visual area. The lowest device on the shoes will have 15 degrees. Those two things, based on your graphic explanation, they will cross. I assume they will cross if this is far away enough. So
yeah,
on some spot will be no blind zone.
There will be no. That's true.
So you're probably gonna have to say something on chest.
Right.
15 degrees.
Yeah. The reason that there actually will be no overlap because the range of these rangefinder devices. This is the cheapest rangefinder that's out there. So the range of these devices is actually only 4 meters. So at the point at which you extend 4 meters outwards, there's no overlap between this L1 and this L2.
Yeah.
One in the middle.
Oh, one in the middle as well. Oh yeah, we can. That could be a use as well. After comprehensive testing, we'll see if the blind spot is usable without having. If the blind spot is still okay to exist using just the popping bar.
Maybe something you can wear on your knee, which will come about.
Yeah. In fact, actually, the main issue with even using the foot sensor in the first place is that because these sonars are fixed, they're not on a gyroscope. They're constantly pointing outwards. So if I were to take a step, I'll actually end up facing the ground, and that will botch the measurement value. So you'll see these very tiny sensors. There's kind of hard to see. These two red sensors are called accelerometers, and what will end up happening is because we're taking a step 1 foot at a time, when you detect acceleration in one shoe, you divert all measurements to the other shoe, and then when you take a step in the right foot, you divert to the left foot. And as a result of that, you'll be able to have constantly normalized, constantly accurate measurements that are constantly being taken. If you're standing like this, it'll take the average of the two, because generally the center of the body is between your 2 feet. If you're jumping up in the air, it will revert to the last known position.
Seriously speaking, one thing, those things connect the devices on the shoes and the tubes. Are you able to turn those things into like a wireless connection to Bluetooth?
Yeah,
So that will be good. That the entire thing will be done.
Yeah, so that's one of the things I'm also working on now. It's hard to build the full thing. Everything's still currently prototypes right now. So a lot of this has been built by my brother and I sitting on the living room floor. But the future, what I hope to do is that I actually have clip-ons that clip on to both the shoes and even the glasses, and it can be a wireless connection via Bluetooth. But that will take more time to produce as well. So right now we're just focusing on creating the eye level the eye level device first, in addition with the cane. And in the future we can move on into looking at a full wireless connection. But definitely, yeah. So what ends up happening is we're able to create this device, and this device is able to give you a full, comprehensive understanding of where things are in relation to you and what those things are. And using that the combination of both technology and user feedback, we're able to create more robust and useful devices that can help you. So this started out 4 years ago in you can do it.
Yeah.
Yeah.
Sorry about that. You okay? Go ahead.
So this started 4 years ago in India. And now this past summer, I visited India again to test my device in many places. This is the Narendra Vidyalaya School for the Blind. And there I was testing my device. As I saw people using it there, I felt confident knowing that this device can actually go to help change lives. So I hope that today, with this talk, we can go out and invent inventions that can change lives, invent inventions that will help millions of blind people see again. Thank you.
So while